So this is box B here, derivatives of exponential functions. So if you watch the lesson for part A, we've already gone over this a little bit, but we know that if our function is e to the x, our derivative is also e to the x. So this is sort of the simplest derivative rule that you're going to have to know. Okay. Where it becomes tricky is if your function is a composite function. So instead of just e to the x, you have e to some function of x. We'll just call that g to the x. In this case, we have to use the chain rule. So our derivative is going to be our original function. So it's our outer function is e to something, which is just, again, e to something. So we do our original function, e to the g at x. Okay? And then we multiply that by the derivative of our inner function, which is g of x. So we just multiply this by g primed at x. Okay? So it's our original function, whatever we see, multiplied by the derivative of what is in the exponent. Okay. So let's take a look at a couple of examples here. First one here, y equals e to the 5x. If we want to go through the steps here, this is obviously one where we have to use the chain rule. Our function g of x, which is our inner function, is just 5x. So our derivative, y primed, is going to be our original function, e to the 5x, times g primed at x, or the derivative of what's in the exponent. Derivative of 5x is just 5. So this is going to be times 5. All right? So this is 5e to the 5x. And because exponential functions have this property where the original function always appears in the derivative, you're sometimes asked to express your derivative in terms of the original function. So our original function here is e to the 5x, which appears right here. That's just y. So we could also write this as 5y. Just identify where the original function appears and sort of write that in. All right, so let's look at next example here. Give myself a bit more room. All right, our next function here is y equals 7e to the x squared. Again, we're going to be using chain rule. Our inner function, g to the x, is, well, it's what's up there in the denominator, x squared. So our derivative is going to be, let's see, 7 e to the x squared, so our original function, times the derivative of our exponent there, or our g to the x. So derivative of x squared is just 2x, so it's going to be multiplied by 2x. And then we can simplify this. 14x e to the x squared. Or, if we wanted to express it in terms of y, doing that, y was 7e to the x squared, so we've got y right there. This would be 2xy. Our last one here, where we start to get a little bit complicated. 6x to the power 4 times e to the 3x plus 7. Okay. What are we going to need to do here? What rule are we going to need to use? Yeah, product rule, and then the chain rule to do the derivative of that exponential function. Sorry about that. So let's start by, well, let's just identify what our two functions are going to be here. We'll call this one u, we'll call this one v. And if we're going to do product rule, remember that it's derivative of u times v plus u times the derivative of v. So our derivative of u, this is just power law here, so we get 24x cubed. Multiply this by our v function, 3x plus 7, plus our original function here, our original u, so 6x to the power of 4, times, what is the derivative of v going to be here? V is an exponential function, so we're going to have our original exponential function, 3x plus 7, times the derivative of what's in the exponent, which is just 3. Okay. So now we should look at what's common to these two terms and try to factor it. So we can definitely factor out e to the 3x plus 7, which is going to leave us with 24x cubed plus 18, because that 6 gets multiplied by the 3, 18x to the power of 4. Okay? And is there anything else we can factor out now? Richard? Yeah. So we can do 6x to the power of 3, e to the 3x plus 7 times 4 plus 3x. Okay. Which is our derivative there. If we wanted to write this in terms of the original function, our original function was 6x to the power of 4, e to the 3x plus 7. We've got 6 to the power of 3, e to the 3x plus 7 out front. If we were to, now, I mean, you would stop there unless it told you to write it in terms of y. If it did tell you to write it in terms of y, you would, you need another x there. You need this to be 6x to the power of 4, e to the 3x plus 7. But if I've multiplied that by x, I also have to divide it by x. So those two, the x's, when I did that division, would give me the x cubed back. And this would still be times 4 plus 3x. So this thing up here in the numerator is my y. So this would be y over x times 4 plus 3x. All right. So let's take a look at an example, sort of an application type question here. Find the equation of the tangent to y equals x e to the minus x at x equals 1. Okay. So this is the kind of question that you've done, I don't know, at least 20 times by now in the course. Okay, finding the equation of a tangent to simplifying. The only difference is what derivative laws we have to apply. So what's our first step in a question like this? Determine g at x. Okay. So we've got g at x equals negative x for our exponential function. What else do we have to notice about this function that we're given? What rule are we going to have to use when we're doing this derivative? Chain rule and the product rule, because it's x times something. So let's get our derivative here. Y primed is going to be derivative of this, which is just 1 times our second function, plus x times the derivative of e to the minus x. So that's going to be e to the minus x times the derivative of g to the x. So g to the x should be negative 1x. So we've got to multiply that by negative 1 there. And then we can simplify. E to the minus x minus x e to the minus x. Have I done this correctly? Okay. Where do we want to go from here? Okay. Now what do we want to do? Yeah, we want to evaluate this at x equals 1. Derivative gives us the slope of the tangent, so we want the slope of the tangent at x equals 1. So at x equals 1, y primed is going to equal e to the minus 1 times 1 minus 1, which is 0. So what does this tell us about our tangent line here? It's non-existent? It's horizontal, yeah. Yeah. So it's horizontal. Okay, so now what else do we need to do if we're going to get the equation of this thing? Okay. We can put in our slope is 0. So y is just going to be b. How do we figure out b now? So go back to our original equation here. So we've got y equals x e to the minus x. If x equals 1, this is 1 e to the minus 1, which is just going to be 1 over e. So if y equals 1 over e, that's going to be our equation. I mean, we put in y equals 1 over e. That tells us that b is 1 over e, so y equals 1 over e is the equation of our tangent. Okay? This is the equation of a horizontal line because it's just y equals a constant. Okay? One more example of a kind of question that you've done about 1,000,000 times here. Given a function, y equals e to the x over x. We want to take the derivative. We'll express it in terms of y. And then we'll find the absolute maximum and minimum over the domain, negative ln 2 to ln 2. So let's get our derivative first. What do we need to do in order to take our derivative? Nick? Okay, if you want to rewrite it as a product instead of a quotient, okay? And then we're going to use product rule here. And no, actually we don't need chain rule. Just product rule. So what are we going to have here? We're going to have derivative of, let's do u and v. Derivative of u is e to the x times v, which is x to the minus 1, plus u, which is e to the x, times the derivative of v, which is going to be negative 1 times x to the negative 2. Okay. What should we do with this thing now? Okay, so we can factor out e to the x and x to the negative 2, which is going to leave us with x plus, oh, and it's going to be minus because that negative 1, so x minus 1. So this thing we can rewrite as e to the x, x minus 1, all over x squared. If we wanted to express this in terms of y, let's see. Y is e to the x over x. So this is kind of like e to the x, x minus 1 over x times x. And this part right here is my original function, y. So we could write this as y times x minus 1 over x. Okay? And this would be our answer to part B. Okay? But part C is what we're really interested in here. We want to find absolute maximum and minimum. Okay? So if we're going to find absolute maximum and minimum, what are we going to do first? Or what are the steps that we're going to follow here? Okay, so to look for our critical numbers, okay, by setting the derivative equal to 0 or finding the points where the derivative does not exist. So that'll give us a local max or local min, and then we also want to check our two endpoints because we have a restricted domain. So let's start with derivative equal to 0. Let's see, our derivative is going to be equal to 0 where our numerator equals 0. So we've got 0 equals e to the x times x minus 1. So we have two possibilities here. Well, 0 equals e to the x and x minus 1. Sorry? Yeah. Yeah, I'm coming back to this expression right here. Okay? So I'm looking first at where our numerator equals to 0. Okay, so I'll just call this critical numbers. Okay. Our derivative equals 0, where our numerator equals 0. I got two possibilities. I'll solve the hard one here. X equals 1. I'll leave the easy one for you guys. 0 equals e to the x. What's the solution to that? Why is it impossible? Yeah, there's no solution here. The other way to think about it is like visualize that function, e to the x. Okay? It goes like that. Does it ever equal 0? No, it never reaches that, that x-axis. So there's no point where our y value is going to equal 0. So we have one critical number right here at x equals 1. What about where y primed does not exist? Yeah, where x squared equals 0 or at x equals 0. Now, is this a critical number? Well, if we go back to our original function, e to the x over x, what happens at x equals 0? Mm-hmm. So we're dividing by 0, which is bad. So basically, this point, x equals 0, is not part of our domain. So this critical number that we got here isn't really a critical number because it's not in the domain. Okay. So it's not valid as a local maximum or local minimum. Okay. These things that aren't in the domain, in the last unit we saw that they could be vertical asymptotes, but because we're looking for maximum and minimum here, we're just going to ignore that point. So we only have one point that is a local max and min, x equals 1, and we also want to check our two endpoints, ln 2 and negative ln 2. Okay? And because all we want is the absolute maximum and minimum, if we just find the y values that correspond to each of these points, that should tell us what's the absolute max and what's the absolute minimum. So let's just do that. If x equals 1, y equals e to the 1 over 1, which is just e, which is, I should say, it is approximately 2.71. Okay. If equals ln 2, we get e to the ln, and that's not a ln, that's an h, but e to the ln 2 over ln 2. Okay. E to the ln 2 is just going to be 2 over ln 2 because we have an exponent and a logarithm with the same base, so they sort of cancel each other out. And 2 over ln 2 is just going to be, I get that it's about 2.88. And if we go to negative ln 2, we get e to the negative ln 2 over negative ln 2. How can we simplify this? Well, we can think of it as e to the ln 2 all to the negative 1. Okay, using our power law of logarithms, bringing that coefficient out front up into the exponent. Since we know that e to the ln 2 is just 2, we get 2 to the negative 1, which is just 1 over 2. So this is going to be negative 2 ln 2. Or sorry, 1 over negative 2 ln 2. Which we can just work out what that is. And we get that it is, well, actually I don't have a value for it. I don't know what the value is. But I know that this is going to be my smallest value because it's the only one that's negative. All right? So it's going to be negative something. What is it going to be? X punching it in here. Da, 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 da.
Negative 0.721.
Okay. So just by looking at these numbers, we can tell that this is going to be our absolute max. And I'll just say this is our absolute max. Max is right here. And this guy down here is going to be our absolute min. And I'll spell absolute correctly this time. Yeah, so just by checking those values, we can tell which is our maximum, which is our minimum. Yeah.
Oh, sorry, never mind. I was going to say local.
Yeah. In this case, we're not really interested. If it had asked us to find the local max and the local min, then we would just consider this point right here, x equals 1, and we would apply the second derivative test to check and see whether this is a local max or a local min and classify it that way. But because they were asking us for the absolute, we're just checking our endpoints and our turning points. Okay. And that's all there is.